Today, I'm going to cover Avogadro's law and also combined gas law. To start with, we're going to cover the combined gas law. Combined gas law is basically a combination of Boyle's and Charles' law into one expression. To make this work, we will have to keep the amount of gas constant, and mathematically, this is equivalent to P1 times V1 over T1. That's equivalent to P2 times V2 over T2. So here's the first practice problem. A gas at 122 kilopascal and 30.0 Celsius fills up a flexible container with an initial volume of 2.00 liters. So I'm going to basically first write down my variables. So starting with the first one is going to be the pressure. So I'm going to put the P1 is 122 kilopascal. And at this condition, the temperature is 30.0 Celsius. And the initial volume is 2.00 liters. So that is my V1. And then the temperature is raised to 80.0 Celsius. That's my T2. And also the pressure increased to 440 kilopascal. Here's my P2. And my T2 was 80.0 Celsius. And I'm looking for what would be the new volume, which is V2. Based on these given variables, we know that we have to use the combined gas law. However, the temperatures are given in terms of Celsius. So you'll have to first convert this temperature into the Kelvin. Please keep in mind, for every gas law, you're going to have to use a Kelvin temperature. If you use Celsius, it's not going to work. So I'm going to go ahead and convert the Celsius into the Kelvin, and the conversion factor is to add 273. Now, 30.0 has the significant figures all the way down to the 1/10. Right here, this one is a significant figure. When you're adding a 273, the 273 itself is not going to affect the significant figures. So you're going to have to report your answer to the least accurate measurement, which is 1/10. So your answer would be 303.0 Kelvin. Now the second one is the same, 80.0 Celsius plus 273, and the number would be 353.0 Kelvin. Now I'm going to go ahead and express the combined gas law, and then I'm going to have to rewrite this equation in terms of V2. So using the literal equation, I'm going to go ahead and arrange my variables again, and now V2 is equivalent to P1 times V1 times T2 over T1 times divided by P2. Now I'm going to go ahead and plug in my numbers, and once you plug in all the numbers and then reporting to two significant figures, because you have 3, 3, 4, 4, 2 significant figures. So final answer would be two significant figures, 0.65 liters. Practice question number 2. The pressure of gas is reduced from 1200.0 millimeter Hg to 850.0 mmHg. So I'm going to go ahead and write down my P1 initial pressure, right? It came from, reduced from 1200.0 millimeter mercury all the way down to 850.0 mmHg. And then my volume has also changed from 85.0 milliliter to 350.0 milliliter. So my volume has changed from here to there. Now, what would be the final temperature if my original temperature was 90.0? So my original temperature is 90.0 Celsius. I'm looking for the final temperature. Again, based on this information, we have to use combined gas law. And also, again, since the temperature is given Celsius, we got to convert this into Kelvin again by simply adding 273. Again, 90.0 Celsius also has the act of measurement to the nearest 1/10, and you're adding a number here, so addition rule applies. So, but 273 itself doesn't affect your significant figures because this is just conversion factor. So your reported number for Kelvin should be 363.0 Kelvin. Now, the combined gas law that looks like this: P1 V1 over T1 is equal to P2 V2 over T2. This time we are solving for T2, so you'll have to rearrange the equation to solve for the T2. T2 therefore would be P2 V2 T1 over P1 V1. Now plug in the numbers for the numbers we found on the left side, and then report your answer to the least accurate, at least the number of significant figures, because it shows multiplication and division, right? Then you have to round your answer to the least amount of sig fig. So there's a 4, 4, 4, 5, 3. So 3 would be the least amount of significant figures. So your answer would be 1060 Kelvin using 3 significant figures. And if you need to convert this answer to the Celsius, well, since the temperature I gave it to you was originally 90.0 Celsius, I'm going to go ahead and answer my final answer using the Celsius. So we're going to have to now convert the Kelvin into the Celsius by this time subtracting 273. Now, again, be careful with the significant figures. Your initial answer was only accurate to the nearest tens, right? This one's significant figure, significant figure, significant figure. That last zero is not a significant figure. So your final answer must be also only be accurately measured to the nearest tens. So once you subtract these two numbers and round your answer to the nearest tens, that's going to be 790 Celsius. Now, here's the next gas law called the Avogadro's law. Avogadro's law is basically saying the volume and the number of moles of gas are directly proportional. And to make this work, you're going to have pressure and the temperature hold constant. Mathematically, this is equivalent to V1 over N1 is equal to V2 over N2. So first volume over number of gas moles, N, that's what N stands for, is equivalent to V2 over N2. So basically put it this way: more gas you put into the container, right, assuming the pressure and temperature are held constant, right, more gas means that you need more volume. So here, right, for example, let's say that you have 1 mole of gas, and then that occupies exactly 22.4 liters. And then if you double your number of gas, right, that means more gas into it, then your volume has to also double, which is 44.8 liters. Okay, so now let's go ahead and do a practice problem. A 20.0 liter tank contains 3.5 moles of helium gas. Okay, so first of all, the given volume is a 20.0 liter, and the first amount of gas is going to be 3.5 moles. So 3.5 moles of whatever gas, or helium gas, is occupying 20.0 liters right now. And if I expand the tank, the volume, right, if I make the size of the tank larger to 43.5 liters, then how many moles of gas can be put into this new tank? Okay, based on this given information, we know we have to use the Avogadro's law. Avogadro's law looks like the V1 over N1 is equal to V2 over N2. Since we are solving for the N2, I'm going to go ahead and rearrange the equation, right, to solve for the N2, which is V2 times N1 over V1. Now I'm going to plug in my numbers: 43.5 liters times 3.5 moles divided by 20.0 liters. And that, again, this is multiplication division only, and you have to report your answer to the least amount of significant figures, which would be 2. So your answer is 7.6 moles total. Okay, here's the second practice problem. A 40.0 liter tank contains 5.3 moles of ammonia. So this time the first volume, the initial volume, is 40.0 liters, and this one contains exactly 5.3 moles of gas. And calculate the new volume if you are going to be adding 2.5 moles ammonia is added You're going to be adding this much to the original tank while the temperature remains constant. Now, think about this very carefully. I said I'm going to be adding 2.5 moles to the original tank. So my final moles, the N2, is not going to be 2.5. I'm going to be adding 2.5 to the initial amount of gas, 5.3 moles. So adding these two numbers and obeying to the significant figure rules, you should be getting now 7.8 moles instead. Now, if you're going to be adding more gas into this tank, right, let's go ahead and find out what's going to be the new volume. Okay, we're going to be using the Avogadro's law again, and V1 over N1 is equal to V2 over N2. We are solving for the new volume this time, so that's V2. That's equivalent to V1 times N2 divided by N1. Plug in your numbers, reporting to the two significant figures, and that's equivalent to 59 liters.